All right, let's go ahead and take a look at some typical problems that you might see on your upcoming exam. So remember, our exam is coming up at the end of this week, and the chapters that we'll cover is essentially 1 through 5, but of course we didn't really spend a whole lot of time in chapter 5. Is pretty much just friction was the only topic that we covered. So most of what you want would be in chapters 1 through 4, covering our kinematics, our two-dimensional motion, and our beginning of looking at this forces stuff. Let's take a look at a couple simple problems. That will be helpful to you for the exam. So we'll start with the easy stuff and kind of make our way up in difficulty as we go from there. So we'll say our first problem we can say is we have two continents are drifting apart at about 3 centimeters per year. And then what we want to know is how long until the continents are another 500 kilometers apart from one another. So this is just a very simple one-dimensional kinematics problem, right? We have these two things. The distance is increasing with some sort of rate. We want to know how long it's going to take for them to be another 500 kilometers apart from one another. So we know that our speed that we have is going to be 3 centimeters per year. We can also write this as 0.03 meters per year. I'm not going to even bother to put it in meters per second. I'll just give I'll leave it in meters per year, and I'll figure out a time in years. Our distance that we have, we know how long it's going to take them to drift apart from one another. 500 kilometers or 500,000 meters, right? So then we just have a very easy distance equals rate times time. Solve for the time that we want. So we have our distance is our 500,000 meters. Our speed is our 0.03 meters per year, right? 3 centimeters per year. And so what we get is about 16.7 million years. So again, just a very simple distance equals rate times time. There's no acceleration or anything that we have to worry about. We're just making some nice simplifying assumptions here. We're given our speed, we're given our distance that we want to go, how long it's going to take us to get there, right? Okay, so we'll do another one. We'll move on. We'll look at some of our two-dimensional vector addition that we have. So we can say in this case, we're going to be driving along an inclined road, and we're going to notice a sign that has indicated our elevation has increased by 530 feet. And we notice the sign after we've driven, looking at our odometer, we've seen that we've driven 1.2 miles. And so what we want to know is what is the angle of the road. So again, this is just looking at our two-dimensional stuff. We are going up at some sort of slight incline. Right, so here's our road. It's a little bit exaggerated, right? And so we've gone up 530 feet, and we have driven a distance along the road of 1.2 miles. And so what we want to know is what is this angle? So you can see pretty clearly we can have sine of theta is going to be equal to, right, the sine of this angle gives us the ratio of the opposite over the adjacent, right? So if we have here's our right triangle that we're setting up. So yeah, the sine of this angle is equal to the ratio of the opposite side, 530 feet, divided by 1.2 miles. Let's put these, make sure we have them in the same units, right? We need this ratio to have our units cancel out. So 1.2 miles is equal to about 6,340 feet. So we have this. Then of course what we want is the angle. So we take the inverse sine of this of 530 by 6340, and this gives us an angle of about 4.8 degrees. So just kind of almost kind of like a trig problem, right? We're just kind of making sure we understand the different terminologies, right? Our vertical distance has increased by this 530 feet. We have driven along this road 1.2 miles, right? So it's not the horizontal distance that we've covered, right? The actual distance that you've traveled in your car that your car will measure would be this 1.2 miles going up this slight incline that we have here. So we do that, make sure we recognize sine of theta equals 530 over 6340, take the inverse sine, and solve for our angle. Okay, so the next one that we can do then, we can start looking at some basic projectile motion problems. So we have, in this case, we have a river flowing at 3.6 meters per second, flows over a waterfall That is 108 meters high. So we want to know is how fast is the water moving when it gets to the bottom. So this is a projectile motion problem, but it's since we have the water flowing off a river, looks like this, something like that. Um, so we have our river flowing, we hit this waterfall, and we kind of fall off the edge here. We can assume that this is a zero launch angle problem, right? So we are launching, in this case, the water is our projectile, right? And it's going to arc off this cliff. It's going to fall 108 meters. And so what we want to know is how fast is the water moving when it gets to the bottom? So what is the overall speed, right? So we don't need to worry about too much about the direction. All we're asked for is what the actual speed of this water is when it hits the surface below. Okay, so we'll keep this in mind. This is our kind of our initial velocity. This is also our initial x velocity, right? But this is our initial horizontal velocity. So we know that this is going to remain the same, right? For our projectile motion problems, there's no acceleration in the x direction. There's only acceleration in the y direction because it's gravity pulling it straight down. So we are going to fall vertically 108 meters. So we know for our final velocity, we need both the x and y components. So that's essentially what we're trying to find. So let's look at what our initial velocity components. Our initial velocity in the x direction is 3.6 meters per second. Our final velocity in the x direction also going to be 3.6 meters per second, right? Again, because we have no acceleration. So how can we figure out what this final velocity in the y is? So we have final velocity in the y is what we need to find, and then we can very simply use our Pythagorean theorem and figure out what our overall final speed is. So let's look at it this way. We have delta y equals 1 half gt squared. So when we look in the y direction, our initial y velocity is 0, right? We're launching horizontally off this. This water isn't being pushed up. It's not being pushed down. It's just falling off this edge as it's kind of going off this cliff, right? So it's moving horizontally, falls off the cliff. So the initial velocity in the y direction is 0, right? That's what I mean by 0 launch angle. But our delta y is going to be what? It's going to be this 108 meters. Our g is going to be 9.8, and our time is what we don't know. So you can very simply solve for that. Square root of 2 delta y divided by g. This is in the square root. And so the time that we get is about 4.7 seconds for this water to fall. So with that, we can then very simply solve for v final in the y direction. The initial speed in the y direction is 0. So we just have g times t, right? We're accelerating at 9.8 meters per second for 4.7 seconds. And we get a final velocity in the y direction of about 46 meters per second. So finally, we have our final velocity in the y, we have our final velocity in the x. Our overall final velocity is then going to be x squared plus the final y squared, take the square root of that, and we get something very, very close to this, right? We're moving much faster in the y direction than we are in the x direction. We are still moving a little bit in this x direction. So if you do this, what you'll get is about 46.1 meters per second, right? So again, zero launch angle problem. The time that we spend in the air is you can find very quickly based upon looking at the y direction, how far we have to fall. The x direction, we have some initial motion. There is, when we have this zero launch angle, there is no motion initially in the y direction, right? So we just have our initial velocity is 0, and it makes solving for the time very simple in this case. Okay. Let's look at a relative velocity problem. So we can say in this case we have a boat is traveling upstream at 4 meters per second relative to the water. So we have the speed relative to the water. We also know that the stream is flowing at 1.2 meters per second. And so we want to know is how long will it take for this boat to travel 750 meters along the shore, right? So again, for these relative velocity problems, to have our speed relative to our stationary frame, in this case, the speed of the boat relative to the ground, it's going to be equal to the speed of the boat relative to the water, this would be prime, plus however fast the water's moving, right, the v of our frame. So in this case, we don't know this one, but we want to know it, right? We want to know how long is it going to take us to go 750 meters. The only way we can know that is if we have how fast we're going relative to the ground. So we have v equals, what's our speed relative to the water? 4 meters per second. What's the speed of the water? In this case, it's going to be minus, right? We're going upstream, right? So if I were to draw my picture and I have my little river here, the water is going, the frame equals 1.2 meters per second. Then we have our boat going upstream. V prime equals 4 meters per second, right? So we're just going upstream, so it's just going straight back from us. So this is even easier than some of the homework problems that we had. We just have this one-dimensional case here. We don't need to worry about the x and y directions. We just have this one direction that we're going to worry about. So we have 4 meters per second minus 1.2 meters per second. This, of course, gets us a speed of 2.8 meters per second. Now, again, we just have a very simple distance equals rate times time. X equals v times t. T equals x divided by v. So we have our 750 meters divided by our 2.8 meters per second relative to the ground, and we get is about 268 seconds, right? Okay. So we'll do one with our forces, and that'll be a little bit more complicated than some of these others that we've seen. So let's see, make sure we understand how to draw our free body diagrams and set up our Newton's second law equations, right? So we have a box. It's going to slide down a frictionless ramp. So we don't even have to worry about friction in this problem. We just have a box sliding down some sort of ramp. We're going to say if the ramp descends a vertical distance of 1.2 meters and it takes the box 7.3 seconds to slide down the ramp, what is the angle of the ramp? And we can also assume, well, we have this note here, assume that the box starts at rest, right? So we're given how long it takes this box to slide down the ramp. So let's draw our picture here. It's going to look something like this. We want to know what this angle is. We don't know what it is. We have some sort of box, though, that's going to be sliding down the ramp. So we've looked at this problem before. You might already remember what the acceleration is. Let's go through all the steps to make sure to derive what our acceleration is going to be. And then from there, we actually need to do a quick kinematics problem with this one. Okay, here's our box sliding down our frictionless ramp. What are all my forces on this? I'll start with that. We have gravity. It's going to be pulling straight down on our box. And then we have our normal force. It's going to be pushing it up and away from the surface, right, perpendicular to the surface. So with this, then we can start writing our Newton's second law. Just make sure you remember this is the same angle here, right? This angle theta and this angle theta are the same. Again, you can kind of visualize, imagine, right? We're not tilting our coordinate frame at all. Our angle is 0, right? So then this vertical lines up with the vertical of the direction gravity is facing. But as we increase this one here, as we make this ramp steeper, right, this one gets pulled away by the same amount. So we have this angle here and this angle here are the same. Let's go ahead, let's put our coordinate system again. Let's tilt our coordinate system so we do have this box sliding down the ramp. Let's go ahead and put the x direction down the ramp. So I'll put this as my y, and I'll put this as my x direction. So we know as far as what this box is going to be doing, essentially what we need to do is we need to figure out the acceleration of this box, right? So we have our F net equals ma will help us with that. And from there, then we can use this time. We can figure out, how long this ramp is and some other things, right? We have, what is it? We have the vertical distance is 1.2 meters. So we know that this height is 1.2 meters. We do not know the length of this ramp. If we do, we can figure out the angle or vice versa, right? We can either figure out the length of the ramp or we can figure out what the angle is. That would figure out the angle. Ultimately, what we want is, we want this angle though, right? Okay, so we have this. We have our gravity pulling straight down. We have our normal force going up off the ramp like this, perpendicular to it. So let's look at just in the x direction. We know that the normal force will cancel out with some component of gravity. We're not worried about that. There's no friction in this case, so we don't need to worry about that. So let's look in the x direction. Let's add up our forces in the x direction, right? What we can say is this. In the x direction, we have mg times the sine of theta, right? That gives us this component here, right? The opposite side of this angle. This component of my gravitational force, that's what's going down the ramp. Mg sine theta, and that's it, right? That's the only force in the x direction. So this must be equal to m times a. So of course, this is going to tell us that our acceleration is equal to g sine theta, right? So now that we have this, right, we know what our acceleration is going to be. At least in terms of this angle, right? But we don't know exactly what the angle is yet. But how can we set up a kinematics problem now to figure out this angle? So we've done our Newton's second law, right? We have our F net in the x direction equals our mass times our acceleration. So let's go ahead and move on. Now we can plug this acceleration into our kinematics. So we have this one-dimensional kinematics problem. We are starting from rest. We are traveling some distance. I'm going to call this distance L, right? That we go down the ramp. So we traveled down the length of the ramp. We have no initial velocity, so we just have 1/2 times x times a times t squared. So in this case, we have g sine theta is our acceleration times t squared. So here's what we know. We know our time, right? We have our 7.3 seconds. We know our uh, gravitational constant, 9.8 meters per second squared. We know our 1/2. We don't know this theta, but we also don't know this L. So how can we relate this theta and this L in some way so that we can actually plug in and solve for one or the other? Let's go ahead and just write our equation. What we must know has to be true based on our trig, right? The length of this ramp, right? This overall, here's our L, right? The actual length of the ramp, the hypotenuse length of this ramp is, how is it related to this? We know that L over 1.2 meters, right? Oops, sorry, hold on. This is actually equal to 1 over the sine of theta. I got it backwards. So let me write this. Let me make sure I write this clearly. So this is correct, just to be clear. But what I should say is this: sine of theta is equal to 1.2 meters divided by the length of the ramp, right? The opposite over the hypotenuse, in this case, the hypotenuse is L. So this is true. It's just written a little bit awkwardly, and I apologize for that. But we do have this. This might make a little bit more sense to you, right? Sine of theta equals 1.2 meters over L, right? So from this, though, we can solve for L. We can say that L is going to be equal to 1.2 meters divided by the sine of theta. So now we can plug this in to this equation here. So we have 1.2 divided by sine of theta equals 1/2 g sine of theta times t squared. Now we have one equation, we have one unknown, we just have to solve for our theta, right? So let's go ahead, let's rearrange, let's move this sign over. So we have 1.2 meters, make sure I don't go off the page here, equals 1/2 g, so we multiply both sides by sine of theta, g sine squared of theta times t squared. Now I want to get this by itself, so we have sine squared of theta equals, let's move all this stuff over. We have 1.2 meters times 2, right? Divide by 1/2 times 2, and then divide by g t squared, right? Okay, so take the square root and then take the inverse sine, and here's what we get. We have theta is going to be equal to the inverse sine of the square root of all of this stuff, right? Take the square root of this side, we just have the sine of theta. Take the square root of this side, take the inverse sine, so we have square root of 1.2 meters times 2 divided by g times t squared. And again, remember our t we know is, it's up here, 7.3 seconds, so we're given that one. So with this, we can now just plug this into our calculator, and we get an angle of about 3.9 degrees, right? So yeah, so this was kind of a combination problem of a couple different concepts, right? We started with our Newton's laws, with our Newton's second law in particular. We drew our free body diagram. We labeled all the forces. We split our forces up into x and y, but we knew we only needed to worry about the x component. We solved for our acceleration, and with that, we have our acceleration, and that will allow us to solve our kinematics problem. It's a little bit awkward because I gave you the vertical distance, right, instead of the actual length of the ramp. But simple enough, we can just relate what the vertical distance is. Oops, sorry. Relate what the vertical distance is to the length of the ramp and plug it in. Make sure that we have one equation, one unknown. Solve for our angle theta, right? So it's about as complicated as it would ever get for any of the exam problems that I will give you on your first exam.